In this video, we're going to be talking about hydration reactions of alkynes. So there are two types of hydration reactions of alkynes, and they are acid-catalyzed hydration and hydroboration-oxidation. Both of these should be familiar because you do the same thing with alkenes, but there are several key differences with these that you should be aware of. So, similar to hydration of alkenes, acid-catalyzed hydration is going to add a hydroxyl in the mark position, or the most substituted position. So this is the same. And this is what this enol is right here. This is if I just stuck a hydroxyl on the mark position, but for alkynes, this is not the final product. This is just an intermediate step, and it actually becomes a ketone. So this ketone right here is going to be the final product. And this transformation from the enol to the ketone is called acid-catalyzed tautomerization, and this is super important to the mechanism of acid-catalyzed hydration of alkynes. So if you're ever asked to draw out the mechanism, you need to know this part, and that's what the next slide is going to be, is we're going to look at the mechanism for that. So something else you should notice is that the reagent is a little bit different than acid-catalyzed hydration of alkenes. For acid-catalyzed hydration of alkynes, we are going to use H2SO4, H2O, and then we're going to have a mercury compound right here, and this is going to act as a catalyst to speed things up. So let's just go through this. We have our alkyne right here. We have a different reagent, and that is going to add the hydroxyl mark, but this is going to be an intermediate step. And then it's going to go through a transformation to become a ketone, and the ketone will be the final product. So now we're going to go through the mechanism of acid-catalyzed tautomerization. The double bond of the enol, which is the intermediate, is going to grab a hydrogen from there. It's going to donate its electrons back to the H3O to produce H2O. And then you have a resonance stabilized intermediate. So after this is protonated, you have a positive charge, a carbocation right here, and notice that this is one of the resonance patterns. So this oxygen is going to give its electrons to the sigma bond to fill up the space that the carbocation leaves open. And then that's going to put a positive charge on the oxygen right here. So to get rid of that positive charge, the water that's left over from the acid is going to grab the hydrogen, and it's going to donate its electrons back to the oxygen to fix the positive charge that we have here, and that is how we get this ketone. All right, now we're going to talk about hydroboration-oxidation of alkynes. This is going to add a hydroxyl group in the anti-mark position, and this is very similar to hydroboration-oxidation of alkenes, but this is also similar to what we just saw. What we think is going to be the product is actually transformed into something else, and in this case, it is transformed into an aldehyde, and this is going to be the main product of hydroboration-oxidation of alkynes. So also notice that the reagent is different than the reagent we use for alkenes. We use either 9BBN or CO2BH. These are your two options. And then we use H2O2 and OH-. And you'll see where the hydroxide ion comes in when we talk about the base-catalyzed tautomerization. And the base-catalyzed tautomerization is how we go from an enol to the aldehyde. In the other example with acid-catalyzed hydration, we had acid-catalyzed tautomerization. In this case, we have base-catalyzed tautomerization. So now we're going to go through the mechanism for base-catalyzed tautomerization. We have the enol, which is the intermediate compound, and this is what, like I said, we would expect to see adding a hydroxide to the anti-mark position. But it doesn't stay like this. We use the hydroxide to grab that hydrogen, and this is why it's called base-catalyzed tautomerization, because this base starts out the process. So the base grabs the hydrogen donates its electrons back to the oxygen, and then we have a resonance stabilized intermediate here. So we can see that we have one of the resonance patterns. We have a negative charge that is allylic to the double bond, and then that oxygen pushes its electrons down, and then that double bond puts its electrons on this carbon here, forming a carbanion. That carbanion then grabs this hydrogen right here, and the hydrogen donates its electrons back to the oxygen. Let me move this. And that is where we get to this aldehyde. So when asked to draw only the product of the hydroboration-oxidation reaction of an alkyne, you only draw the aldehyde, not the enol. Remember, this is the enol, and that is what is transformed into the aldehyde in this case. Now we're just going to do a little overview of everything we just talked about. So there are two types of hydration reactions for alkynes. The first one is acid-catalyzed hydration, and that is going to add a hydroxyl group mark, and then that changes into a ketone via acid-catalyzed tautomerization. We then have hydroboration-oxidation, which adds a hydroxyl group anti-mark, and that produces an aldehyde through base-catalyzed tautomerization. And then here I have a list of things that you absolutely need to know for these two reactions. First, you need to know that the reagents are different for each reaction, and they are also different from the reagents used for alkenes. You also need to know the full mechanism for both of these, and you need to know what the products are. The products for these are going to be a ketone for acid-catalyzed hydration, and then the product for hydroboration-oxidation is going to be an aldehyde. You need to know which one adds mark or anti-mark, and you also need to know the tautomerization mechanisms, which is really part of this, because if you have to draw out the mechanism for either of these, that will involve the tautomerization part of it. I hope you found this video to be really helpful. The concepts and information presented in these videos will be true no matter what Organic Chemistry 1 class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.